Hello and welcome everyone. In this video, we are going to talk about memory. So what is a memory? Well, a computer memory is a storage space in the computer where data is to be processed and instructions required for processing are stored. So you can think of memory just like a storage space in the computer, okay? Because we do need to store some data, otherwise the data can be lost. So that's why memory is basically a storage space. So what are different types of memory? Well, there are two types of memory mainly. One is primary memory and second is secondary memory. So in primary memory, you have RAM, which is random access memory, which has DRAM, SRAM, DRDRAM, etc. Then in ROM, which is read-only memory, you have PROM, EEROM, EEROM. So you can read about that in detail. These are out of scope of this particular course. Then you have secondary memory. In secondary memory, you have magnetic memory, which, for example, floppy disk, hard disk, these are magnetic memory. Then you have optical memory, which is CD or DVD, etc. So mainly two types of memories, primary and secondary. Primary would include RAM and ROM, and secondary would include magnetic and optical memory. It could be hard disk, floppy disk, CD, and DVD. All right. Okay, I'll see you in the next video. Hello, everyone. In the previous video, we learned about what is a memory and what are different types of memory like primary and secondary. And in this video, we're going to learn about memory management techniques. So there are two common memory management techniques. The first one is overlay and second is swapping. Okay, so let's start with the overlay. So what is overlay? Well, the concept of overlay states that it will not use the complete program simultaneously, which means whatever part of the program you need, you load it, and once the part is done, you unload it. So in memory management, overlay works in the following steps. First, we divide the program into modules like small chunks. A small portion of the program must remain in the memory at all time for the execution of the programs, while the remaining sections called overlays are loaded as per the need. Now, why do you think we do this? Well, the reason for this is because the space for the memory is limited. And sometimes if we have larger program, it could be difficult to run all of them at the same time. So that is why we use the concept of overlay, because it allows the programmers to write programs larger than the physical memory. And the memory usage really depends on the programmer rather than the operating system. So the programmer manages that. All right, so let's take an example. Well, the best example of overlay is assemblers. Let's say that there is an assembler having two passes, pass 1 and pass 2. Pass 1 code size is 80 KB and pass 2 code size is 90 KB. Now, as I mentioned earlier, there are certain part of the program that always needs to stay in the memory for the execution of different processes. So we must have symbol table, which has the size of 30 KB, and we also must have common routine for both the passes, which is 20 KB. So let's say that we have a main memory and the main memory size is 150 KB. Okay, so assume in the hypothetical situation, we have a main memory size of 150 KB. If we try to run both the programs, which is pass 1 and pass 2, what will be the total? So you can see 80 plus 90 plus 30 plus 20. How much does that come to? Well, it comes to 200 KB. So if we try to run both of them together, which is pass 1 and pass 2, we understand that if our main memory size is only 150 KB, there is no way we will be able to accommodate that. Okay, so what's the solution? Well, the solution is that, well, this is where the overlay concept is useful. So overlay concept says that do not bring the entire program at once in the main memory. Bring it in parts, as in when you need it. Okay, so when pass 1 is needed, you bring the pass 1, then take it out once it's finished executing, and then bring the pass 2. Okay, so bring only one at a time, not together. So let's see how we can achieve that, and let's see if that solves the problem. Okay, so now if we bring pass 1, so pass 1 size will be 80 KB. Again, like I said, symbol table, common routine, these programs need to stay in the memory. And for overlay concept, we need to have the overlay driver also. So 30 plus 20 plus 10, this needs to be there in the main memory for both programs. That's why I put that in both situations. So in situation 1, when we have the pass 1, when we are running pass 1, the total size becomes 80 plus 30 plus 20 plus 10, which is 140, and pass 2 becomes 90 plus 30 plus 20 plus 10, which is 150 KB. Now, if we have the memory partition of 150 KB, then that means that we can run each of these passes individually very easily. Okay, so that's how overlay concept is useful to manage the memory. All right, so let's say that, so we have operating system, we have the resident code, and then we have the overlay area. And overlay 1 can come into the overlay area which has the code and data when it needs to be executed. Once it's done, it moves out, and then overlay 2 comes into the overlay area as in when needed. So one at a time. Okay. Now we're going to discuss the concept of swapping. So what is swapping? Well, swapping is a memory management technique in which any process can temporarily be swapped from the main memory to the secondary memory. Okay. And this is done so that the main memory can be made available for other processes. So let's say we have this main memory and secondary memory. We have different processes. So for now, let's say in main memory, we have process P1 and P2. And in the secondary memory, we have P3, P4, and up to Pn. So different processes. Now, let's say there is a request for P3. And at that point, we do not have the P3 available in the main memory. And okay, so at that point, we don't have the P3 in the main memory. So what is going to happen is we have a concept of swap out and swap in. So in swap out, we'll have one process move from the main memory to the secondary memory. And then in the swap in, we'll have a process move from the secondary memory to the main memory. So over here, process P1 moves out, it goes for input output wait, and process P3 comes in. Okay. And then after the input output operation, when we need, we can again send the P3 back to secondary memory using swap out, and then we can bring in the process 1 back in. So that is your swap in and swap out, right? So that's a concept of swapping. So let's take an example. Let's say that the user process size is 2048 KB, and the standard hard disk, which is the secondary memory, has a transfer rate of 1 Mbps per second for swapping. So if we calculate the time it will take to transfer that process from the main memory to secondary memory, if we calculate that, well, it will be the process size divided by the transfer rate, which comes to around 2048 KB divided by 1 Mbps or 1024 kbps. That makes a total of 2048 divided by 1024, which is 2 seconds. If we consider both swapping and swap out, then it will take around 4 seconds for both swap in and swap out to complete. Hello everyone, in this video we're going to talk about virtual memory. So what is a virtual memory? Well, virtual memory is a memory management technique that provides an idealized abstraction of storage resources that are actually available on a given machine, and it creates an illusion to users of a very large memory. Okay, so it lets the user believe that there's a very large memory available, but ideally just an abstraction of the storage resources that are actually available on the given machine. Now, the operating system maps the memory addresses used by a program called virtual addresses into physical addresses in computer memory. Hello and welcome everyone. In this video, we are going to talk about demand paging. So the demand paging means that the pages should be brought from secondary memory to the main memory only when the process demands it. Okay, so let's say you have a secondary memory and then you have the main memory and you have process A and process B. So let's say when the process demands the page, then those pages can be swapped in and we can swap out the pages that we don't need at that point. Okay, so instead of swapping the entire process into the memory, only those pages demanded by the process are swapped from secondary memory into the main memory. And this is also often referred as lazy evaluation. Okay, so how is the demand paging implemented? Well, when a process tries to access a page, there are certain steps that are generally followed. First, it will try to attempt to access the page. Okay, if the page is valid, which means it is there in the main memory, then it will continue to process the execution as normal. So if the page is already present in the main memory, then no problem, it can continue the execution. Okay. However, if the page is not present in the main memory, then it's going to request for that page. So if there is not enough space available, then it has to go for swap out and swap in. If there was enough space available, let's say there were only 2 pages here and then the rest of the 2 frames were empty, then you could have directly requested that particular page from the secondary memory and bring that into the main memory. But let's say all the frames are already full. So in that case, it has to swap out something. So let's say we have a P4 over here. It's going to swap out the P4 and then it's going to bring in the other page that the system needs. Okay, so if system is requesting a particular page, it has to bring that in, and to make room over here for that page to come in, it needs to swap out the page that is currently not being used. Okay. Now, in case if the process requests for a page and it's not there in the main memory, this is called page fault. Okay, so and you can say that, so if the page is invalid, then page fault trap occurs. It also checks if the memory reference is a valid reference to a location in secondary memory. If not, then the process is terminated, called legal memory access. Otherwise, we have to page in the required page. So that's all about the demand paging, which in a nutshell is basically saying that bring the page into the main memory only when the process demands it, don't bring it otherwise. Hello and welcome everyone. In this video, we are going to talk about thrashing. So what is thrashing? Well, thrashing is a situation when system is spending most of the time in servicing the page faults rather than executing the actual process. So we have learned in the previous videos that when we have main memory and secondary memory and there's a process that is requesting a page that does not exist in the main memory, then page fault occurs, right? And then because it needs that page doesn't exist in the main memory, there's a swap out and swap in happens. For instance, if it requires page 5, then page 4 is going to be swapped, and or if it requires, let's say, page 5, so for instance page 1 is going to be swapped, it goes to the secondary memory and the page 5 comes into the main memory. Okay, so when does the thrashing happens? So if a process is allocated too few frames, then there will be too frequent page faults, and as a result, no useful work will be done by the CPU and CPU utilization will fall drastically. And this drastic fall of the CPU utilization is called thrashing. So let me show you. So let's say in this diagram, we have the CPU utilization, which goes up in this direction. And then we have a degree of programming. So degree of programming means the number of processes at a particular time. So if we are saying increase the degree of programming means increase the number of processes, just a concept. Okay. So the CPU should have as many processes as possible so that the degree of programming is high and our CPU is utilized fully and it's not sitting idle, right? So that is why from here, if you look at the graph, this is a utilization, this is the degree of programming, which means when the degree of programming increases, number of processes increases in the CPU, then the CPU utilization increases. So like this, it goes up like, but at this point, there will be a point that will come, and at that stage, probably there won't be enough frames available. So the swapping would happen. And as soon as the swapping happens, CPU will become busy in getting those pages rather than doing the actual task. And from this point onwards, the CPU utilization will fall down, is because the CPU is busy for doing the swapping of the pages rather than doing the actual task. Okay. So at this point, operating system would think that it needs to increase the degree of programming. So it will start increasing the number of processes. That means that the long-term scheduler would try to load more processes into the main memory to improve the CPU utilization. But the problem is that this will result in further decrease in the CPU utilization, because those additional processes that will be added over here, would trigger another chain of reaction for higher page faults. Okay, because when those pages are not available, if you keep on increasing the processes, but you don't have enough frames available, and if those pages are not available in the main memory, more page faults would occur, which means CPU will get busy in getting those pages from the secondary memory into the main memory, and CPU utilization will continue to fall. So system will continue to increase the degree of programming, but because of those pages not being present in the main memory, thrashing would occur. That means page fault will continue to occur, and system is not actually doing any useful work, but is basically busy doing the page swapping. Okay, so that is the concept of thrashing. All right. So in the next video, we will discuss about what are the techniques we can use to avoid thrashing. Hello everyone. In this video, we're going to talk about what are the different techniques that are available to avoid thrashing. So if you remember from the previous video, thrashing is basically a situation when the system or CPU is spending most of its time servicing the page faults rather than executing the actual process. If you haven't watched that, then please watch it first. So the first technique is working set model, and the second one is page fault frequency. So let's discuss these one by one. So working set model is based on the assumption of locality. So what is locality? Well, locality is a set of pages that are actively used together. And the locality model states that as process executes, it moves from one locality to another locality, just like a function. So, when a function is defined, it creates a locality. Locality is basically the area where you have the set of statements inside of that function, inside of the body of that function, right? So when the function is defined, it creates a new locality. Now, during the execution, when the program control moves from one function to another function, it is moving from one locality to another locality. Okay, so when it's inside of the first function execution, then it's in one locality. Then when it moves to the next function call, then it goes to next locality. So the same concept is there for the locality for the pages as well. Okay, so locality is a set of pages that are actively used together, and processes execute. And when process execute, it moves from one locality to another. All right. Now, it also uses delta working set window. So what is a working set window? Well, a working set window is a moving window, which means at each memory reference, a new reference appears at one end and the oldest reference drops off at the other end, just like the locality model explained just now. Okay, so it'll be clear to you once I give you an example. Let's continue further. It also examines the most recent page reference. And if the page is in active use, it will be in the working set window. And if it is no longer being used, it will drop from the working set window. So let me explain this to you in detail. So let's calculate the working set window of process P1. So let's say there's a process P1. We want to calculate the working set window, working set for the process P1 at time T1 and T2 respectively. Let's say delta equals 10. Okay, and then we're going to create a page reference table for process 1 P1. So these are your pages. So 2, 6, 1, 5, so on up until 4 and so on. So this is the page reference table for process P1. Now we're going to take this working set window. Basically, because delta is 10, we are going to take 10 pages at a time. Okay. And if we calculate the working set window at T1, then this will be all the unique pages. Okay. So what are the unique pages from this set of 10 pages? It's 1, 5, 7, 6, 2. Okay. Because 7 is repeated, so we can only take that once. And then 1, and then 5, 2, 6. Yep. So that's the working set window at T1. Then working set window at T2, time 2. So we take it from here, go up until here. So you can see the unique one is only 3, 4. Yep. So this is the working set window. Okay. At each time. And this is what I was talking about in terms of working set window. Working set window is a moving window. And at each memory reference, the new reference appears at one end and the oldest reference drops off at the other end. Okay, so this is the working set window. Now, so how do we solve the problem of thrashing? How do we solve the problem of those page faults using this working set model? Well, what we're going to do is, so what's going to happen is that to avoid thrashing, if the sum of the working set of all the processes, let's say process 0 to process I, all the processes is greater than the available frames, it's greater than the number of frames available in the memory, then some of the processes will be suspended. Okay, because if the working set is high, then that would mean that, okay, and in case if the sum of all the working set, if the sum of the working sets of all the processes is less than the available frames in the memory, then some of the processes will be resumed. Okay, so that's how it solves the problem of thrashing. Okay, so let's take this example. Okay, first time there were 1, 5, 7, 6, 2 in the working set window, but later on the pages required at time t2 was only 3 and 4, which means some of the pages can be released, they are not needed, right? So we can release the frames that were occupied by these pages. So that's why we are going by this particular, so that's why it says that some of the processes are suspended when some of the working set of all the processes is greater than the available frames in the memory, and the reverse is true. When it's a reverse situation, then we resume the processes. So that's how we solve the problem of thrashing with the help of working set model. Okay. Hello everyone. In this video, we are going to talk about how to solve the problem of thrashing using the page fault frequency. So in the previous video, we learned about what is thrashing. So thrashing is basically a situation where the CPU is busy in servicing the page faults rather than executing the actual process. So in the previous videos, we've learned what thrashing is and how we can use working set model. And in this video, we learn about what is page fault frequency and how we can use it to solve the problem of thrashing. So page fault frequency is a direct approach to handle thrashing that controls page fault rate. Okay, if we take a look at this example diagram, on the top we have page fault rate, so in this direction, and in this direction we have the number of frames in the memory. Now if the page fault rate falls below the lower bound threshold, then some of the frames will be removed to avoid thrashing. Some of the frames will be removed from the process. But if the page fault rate is above the upper bound threshold, which is of here, then more frames will be added to the process to avoid thrashing. So that is basically the page fault frequency method of solving the thrashing. So if the page fault rate is high, then of course we need more frames into the memory so that less number of swapping happens, right? And if the page fault rate is below this threshold, then that means we don't need that many frames into the memory. We can remove some of them. So that's how the thrashing is managed, okay?